Hello everyone, I welcome you all to Physics Wala, and in this session we are going to discuss the next portion related to structure of atom, or I can say atomic structure. First of all, I hope the first lecture of this particular part is clear to everyone. I tried to discuss each and every part in detail, and we discussed about the discovery of fundamental particles as well as the basic idea of cathode as well as anode rays. We discussed about some basic concepts related to the structure of atom, which is basically your Dalton's atomic theory. And also we discussed about certain conceptualization related to electromagnetic radiation. Now basically in this session we are going to discuss much more part related to electromagnetic radiations, as well as we are going to discuss some interesting portion. So definitely this lecture is going to be the building block of atomic structure part, and the topics which we are going to discuss in this particular session is, first one, definitely we are going to start with the electromagnetic radiations, and then we are going to learn about the electromagnetic spectrum. Then we are going to discuss about some important terms which are associated with a particular element, I can say, because we are talking about the basic part of structure of atom. So we need to understand the terms which are generally used with respect to a particular element. Then we are going to discuss an important concept related to black body radiation as well as your photoelectric effect. Then we are going to discuss the last part, which is Planck's quantum theory. Although these two parts are actually very important when we talk about the conceptualization of a particle nature and some deviations from the wave nature. Okay, so let's start with the first part. We were discussing about the electromagnetic radiations, and I told you that basically we are talking about the radiations which consist of electric as well as magnetic field. Those radiations are basically known as your electromagnetic radiations, and in that case the electric field as well as magnetic field, they are perpendicular to each other as well as they are perpendicular to the direction of a propagation. That is the basic idea about the electromagnetic radiation. Now how can you generate this particular part? If I am talking about the movement of a charged particle, I can simply say that charged particle is going to originate the electric field. So just because of the electric field, there is a pulse generating of electric field which corresponds to the generation of a magnetic field. This magnetic field pulse, they are going to generate the electric field, and simultaneously this entire propagation is going to occur, and that's how you can create an electromagnetic radiation. The basic example related to that particular part is your light. So we are going to discuss that part also. And I told you, if we talk about the electromagnetic radiation, they do not require any medium for their propagation, and they always travel with the speed of light. So definitely we are going to correlate the entire part with the speed of light. Now in the same case, there can be many type of electromagnetic radiations depending upon their frequency as well as the wavelength. Generally we talk about the either the frequency part or the wavelength part. The much simpler version is according to their wavelength part. Okay. Now in the same case, we know that we have different type of radiations, like we have a radio wave, we have microwave, infrared, visible, ultraviolet, X-rays, gamma rays. Other than that, we have some more rays which are corresponding to the electromagnetic radiation, but these are the most important ones. Okay, and you can see their wavelength range as well as their frequency range. We are going to establish one relationship between the wavelength as well as the frequency of these radiations with the help of a very simple formula. Okay, I hope the entire previous part is clear to everyone, and if you guys are facing any difficulty, just let me know in the comment box. I'll definitely try to explain that particular question, that particular part in the upcoming classes. Okay, and one thing, one student told me that they want a lecture related to the prediction of a product as well as how to derive the formula of compound. I'll try to make one lecture related to that particular part so that you guys will be able to understand how to write the formula of a particular compound, so that you can calculate their weight as well as their number of moles, and how to predict the product of a particular reaction. Okay, now talking about the next part, we are talking about the electromagnetic spectrum. So the meaning of electromagnetic spectrum is very easy. It simply says that the different electromagnetic radiations, when they are arranged in a decreasing order of their wavelength or increasing order of their frequency, that corresponding part is actually known as your electromagnetic spectrum. So definitely many type of radiations are actually falling under the category of electromagnetic radiations, and when I'm arranging those radiations with respect to their wavelength or their frequency, the decreasing order of their wavelength, or I can say the increasing order of their frequency, then I can say we will get the electromagnetic radiation. I hope this entire part is clear. I hope this entire part is clear. Very simple explanation related to the electromagnetic spectrum. Now in that case, you can easily see that we have different type of electromagnetic radiations. If I talk about the first part, we have the radio waves, we have the microwave, then we have infrared, then we have ultraviolet, then we have a visible part, then we have IR range, we have X-rays, as well as we have gamma rays. And each and every type of radiation has a specific type of application associated with that particular part. If I talk about the radio waves, you all know that we have AM radio, we have FM radio. If I talk about the microwaves, we have a very particular application, which is your household application, a very common machine which you can find in your household, which is your microwave oven that works on the microwave frequency. Definitely in that case, we are talking about the transfer of energy, because if I talk about the waves, basically in case of waves, they carry some certain amount of energy. They are basically the mode of transfer of energy, but without the transference of matter. So these are basically different from the particle nature, because particle nature is very easy to understand. You can actually correlate with particle nature very easily. But in case of wave nature, you need to understand like which part we are talking about. And definitely this energy carrier thing, we have a special theory for that particular part. Generally we talk about the wave can be present at any time, anywhere, but in case of this particular portion, we are going to talk about the actual amount of energy which is present in that particular electromagnetic radiation. Now if I talk about the infrared waves, again if I talk about the mobile phones or your TV remotes, in 2005 or 2006 time, there was a phone, or 2008 I guess, there was a phone of Sony Ericsson, if I remember correctly. Yeah, I had that phone, Sony Ericsson phone. So there was a feature of transferring the data, and that actually works on the IR radiations. And actually the IR radiations or infrared radiations also contain some amount of heat, so they are also useful for the heat part. In the same way, if I talk about the visible region, you know the application very well. You can see me easily just because of the light. So this is the visible part. You can see the different type of colors which are associated with the visible light portion. You have the entire spectrum in that case also, which is known as the 𝐄𝐍𝐆𝐋𝐈𝐿 part. And if I talk about the UV rays, they have another type of application. Currently after the COVID, there are certain instruments which works on the UV rays. You can put your mobile phone, or you can put your valuable things in that particular chamber, and they will provide UV light so that they can kill the bacteria. In the same way, if I talk about the X-rays, we know that we have X-ray machine, as well as if we talk about the analysis of a solid, we have XRD, which is X-ray diffraction. So that particular machine corresponds to the analysis of a solid crystal with the help of X-rays. In the same way, if I talk about the gamma rays, they have application in the radioactivity part. I hope this entire portion is clear, and you can see that if I'm talking about the arrangement, these particular parts are arranged with respect to their frequency or their wavelength. You can see in that case wavelength is decreasing, but frequency is actually increasing. So that is the basic analysis of the entire spectrum part. I hope this application is clear to everyone. Very simple phenomena related to electromagnetic radiation. Okay, now talking about the relationship between the frequency, velocity, as well as their wavelength, the relationship is very easy, and we talked about that particular part. We know that if we talk about the velocity, they always travel with the speed of light. So in that case, we can consider the velocity as a c, which is approximately equal to 3 multiplied by 10 raised to the power 8 meter per second. Okay, we generally know that velocity will be equal to distance traveled by the wave divided by the time taken. Okay. We generally know that this velocity will corresponds to the c part, because electromagnetic radiations have the velocity which is equals to c. Now this 1 upon time, basically number of waves passing through a particular point per second is basically your frequency. So we can say that this corresponds to c. Distance travel, definitely we are talking about the lambda part, because in case of a wave, distance is basically your wavelength part, multiplied by 1 upon t. This 1 upon t corresponds to the frequency. So we can say that c will be equal to lambda into nu. That is the formula, or a very well known formula which you already know, that we have nu is equal to c upon lambda. I hope this entire part is clear. If I talk about the units of a frequency, you know the units are basically second inverse, or I can say hertz. If I talk about the units of c, which is the speed of light, that is meter per second. If I talk about the lambda, definitely it is in either in meters, or if I talk about the very small unit, in that case we generally use nanometer. I hope this entire portion as well as this formula is clear to everyone. Now, talking about a very interesting question, we have the question which is yellow light emitted from a sodium lamp has a wavelength of 580 nanometer. Calculate the frequency and the wave number of the yellow light. Very easy question to understand. So this is the basic question. We have the value of a lambda which is 580 nanometer, or I can write it as 580 multiplied by 10 raised to the power minus 9 meters, because 1 nanometer is basically 10 raised to the power minus 9 meters. Now, from that particular part, we know the value of c, which is 3 multiplied by 10 raised to the power 8 meter per second. So, first part we can calculate, which is frequency, and that frequency is basically c upon lambda. So, we have 3 multiplied by 10 raised to the power 8 divided by lambda, which is 580 multiplied by 10 raised to the power minus 9. I can rewrite it as 3 multiplied by 10 raised to the power 8 divided by 58 multiplied by 10 raised to the power minus 8. Okay, so you can write it as 10 raised to the power minus 8, because 58 multiplied by 10 multiplied by 10 raised to the power minus 9, which will be 10 raised to the power minus 8. Now, you can solve it. That will be 3 upon 58 multiplied by 10 raised to the power 16. That will be hertz. Okay, so you have to calculate the entire part and let me know the final answer in the comment box. Okay, I hope this part is clear. This is the first portion of this question. So, we have to calculate the frequency. Okay, now next part. Second part is again very interesting. Second part is, if we know the lambda, which is 580 nanometers, or I can say 58 multiplied by 10 raised to the power minus 8 meters. So, the wave number is basically reciprocal of lambda. So, we can say that will be 10 raised to the power 8 divided by 58. So, you just have to solve this entire part, because that will be 1 upon 58 multiplied by 10 raised to the power minus 8. So, on upside that will be 10 raised to the power 8 only. So, you can say that will be approximately equals to 100 divided by 58 multiplied by 10 raised to the power 6, and that will be in meter inverse. Okay, so again you have to solve this particular part and let me know the final answer. Okay, that will be your homework. I hope this entire question is clear to everyone. If you have any doubt, just let me know in the comment box. Okay, very simple question. Okay, now talking about the next part. Next question is somewhat related to the same part. Question says calculate the wavelength, frequency and wave number of a light wave whose period is 2 multiplied by 10 raised to the power minus 10 second. So it means it's talking about the time period. If we have the time period, we can say that frequency is basically 1 upon t. So we can put the value as 1 upon 2 multiplied by 10 raised to the power minus 10 second inverse. Okay, or I can say that will be 10 raised to the power 10 divided by 2 hertz or second inverse, or I can say it as 10 means we have 5 multiplied by 10 raised to the power 9 hertz. Okay, so that will be the answer. Now we have the frequency value. What is the wavelength? We can use the formula nu is equal to c upon lambda. From that, lambda will be c upon nu. If we put the value 3 multiplied by 10 raised to the power 8 divided by 5 multiplied by 10 raised to the power 9. So that will be approximately equal to 3 by 5 multiplied by 10 raised to the power minus 1 meters. Sorry, yes, meters, because we are talking about the calculation of lambda only. Okay, so this part is clear. Now the next part is wave number, which is 1 upon lambda. So we can say lambda is 3 by 5. So that will be 5 by 3. That will be 1 by 10. So multiplied by 10, that is 50 by 3 meter inverse. That will be the value of wave number. and that's how you can solve the entire question very easily. I hope this entire part is clear to everyone. Very simple question. Okay, now next question. Okay, next question is again same. So I'm giving you this question as a homework. You can solve this question by yourself. Very basic question. Okay, so this will be your homework. If the wavelength of electromagnetic wave is 3000 nanometer, already given, what will be the value of a frequency and wave number? Just apply the same formula, which is nu is equal to c upon lambda, and wave number will be 1 upon lambda. Lambda is already given to you. I hope this entire part related to electromagnetic spectrum as well as electromagnetic radiations is clear to everyone. Now, if I talk about the basic analysis after that particular part, we need to understand two important concepts. First one is black body radiation, and next one is your photoelectric effect, which corresponds to particle nature. Now, like, how can we jump from this particular part to the next portion? Like, what is the actual relation? How can we correlate the entire part? So, it's very easy to understand. Basically, the entire part related to the wave theory was already established in the classical physics. So, we knew about the basic nature of waves. If I talk about the wave, basically in that case we are talking about the two important applications, which is the diffraction as well as interference. So, these are the two behaviors which are generally shown by a particular wave. Now, when we experimented the same part, when the scientists actually experimented the same part for the electron, so they used an electron gun and they ejected that particular part from a small hole. They found out that that electron, when moving or passing through a small hole, it actually forming a diffraction pattern. It means it's showing a wave nature, but that wave nature is not entirely everything. Because definitely we are talking about the charge particle movement. Charge particle movement means it's going to create electric field, and that electric field is going to create magnetic field. It means they are perpendicular to each other and they are going to propagate. It means we are talking about the electromagnetic radiations. Now the nature of electromagnetic radiation is slightly different, and that entire part was given by Max Planck. So Max Planck was studying the entire part related to the electromagnetic radiations and their energy. So he simply told that if I talk about these radiations, they are not in continuous form. They actually carry a specific portion, a specific amount of energy in the form of small packets, and that he called as a quantum, or we know that that particular part corresponds to the formation of Planck's quantum theory. But he simply said that this entire part of electromagnetic radiation is slightly different from the actual classical wave nature, because in that case I am talking about the energy which is present in the form of small packets, not in the continuous form. Because these are particles definitely, but they are showing wave nature. So something is happening inside that particular part. Now how can we correspond to the entire part related to wave nature, related to particle nature, and how can we correlate these two parts? That part is basically related to the most advanced version of the theory, which is your quantum mechanical model. That part also we are going to discuss, but before that you need to make up your mind that definitely wave nature is something else, particle nature is something else. We have two applications related to each other, each and every part. Wave nature is generally explained already in the classical physics, so we know about the entire phenomena of wave nature. Particle nature they were studying at that particular time, so they had to correlate these two things. Okay, but before that we need to understand some important terms which are associated with a particular element, because they are going to be more oftenly used when we are going to discuss about this particular chapter. So these are basically isotopes, isotones, isobars, isoesters, isodiaphers, and isoelectronic species. I guess some of you already know about all these terms. If you don't know anything about these terms, let's start. Okay, so if I talk about the first part, which is basically isotopes, I can simply say isotopes are the simplest thing. Basically, if I talk about the atoms of elements having same atomic number but different mass number are basically known as the isotopes. And the common example is your hydrogen. In that case, you know that if I talk about 1H1, 1H2, 1H3, first one is a protium, second one is deuterium, and last one is a tritium. So these are the isotopes, because in every case you can see that their atomic number is 1, but their mass number is actually 1, 2 and 3. So what is the basic difference? In that case, you can see the number of neutrons are going to differ. In case of hydrogen, which is the first part, protium, protons and electrons are 1, but neutrons are actually 0 in this particular case. 1 minus 1 will be the number of neutrons, because you know that neutrons are A minus Z. That is the formula for the calculation of number of neutrons, and we already know this particular part. Now, in case of a deuterium, you know that 2 minus 1, so there is 1 neutron present. So, protons are 1, electrons are 1, sorry, neutrons are also 1. Neutrons are also 1. So, that's the important part, typo error, sorry. Okay. In the same way, if I talk about the tritium, again protons and electrons are 1, 1. But in this case, you can see 3 minus 1, which is basically 2. So, in that case, number of neutrons are basically 2. So, you can see there is a difference between each and every part. So, isotopes generally differs in the number of neutrons. Their atomic number is same, but their mass number is different. Mass number generally corresponds to total number of nucleons, or I can say total number of protons as well as neutrons which are present inside the nucleus, which is known as nucleons. Okay. For example, carbon 12, carbon 13, carbon 14. So, again in this case, if I talk about the first part, you know that electrons and protons are basically 6. If I talk about the neutrons, neutrons are again 6. In second case, electrons and protons are basically 6, but in this case, neutrons are 7. In last case, electrons and protons are 6 according to their atomic number, but 14 minus 6, which is 8, so n value will be 8 in this particular case, and that's how you can differentiate the entire part. Again, in case of oxygen, you have a 16, 17, 18. Again, in case of boron, you have 10 and 11. In case of chlorine, you have 35 and 37. So, I hope the entire part related to isotopes is clear. And there is one important application I can say which is very useful in case of isotopes. One is isotopic effect, definitely, and next one is the calculation of average atomic mass, which we already did in the first chapter, which is your mole concept. Now, this particular part is average atomic mass, or I can say this is your average isotopic mass. Okay. Now, what happens in this particular case? The idea is very easy. Let's say we have an isotope of a chlorine which is 35. We have another isotope of a chlorine which is 37. In that case, let's say their percentage abundance is 75% and its percentage abundance is 25%. So, if I am talking about a mixture of chlorine or any type of a molecule of chlorine, I know in that case that the entire part of chlorine does not contain only chlorine 35 or it does not contain only chlorine 37. It contains 75% portion of chlorine 35 and 25% of chlorine 37. So, let's say I am taking 100 atoms of chlorine. I can say 75 atoms has the mass number chlorine 35 and remaining 25 atoms have the mass number which is chlorine 37. That is the basic idea. Now, whenever we are using the mass of chlorine, generally we say that it is 35.5, basically in between these two parts. So, how can we calculate this particular part? It's very easy, that average atomic mass will be equal to mass of first isotope multiplied by its percentage abundance of that particular isotope, and whatever we have to add all these values together, whatever isotopes we have. Okay, so that is the basic part. Now, in this case, if I talk about the same calculation, for chlorine, I can say that average atomic mass for chlorine will be equal to first isotope 35, percentage abundance is 75%, plus next isotope is 37, percentage abundance is 25%. So, if you calculate this particular part, you will get the answer as 35.5 U, and you know, like generally we use this 35.5 U. So, that is the basic meaning. In the same way, if I talk about a basic source, very basic source, you all know that we have graphite pencils. So, generally that graphite pencil actually corresponds to each and every part of carbon. It contains maximum amount of carbon 12, approximately I can say 98.9%, then some portion of carbon 13 and very less portion of carbon 14. So, I can say 1 in 10 raised to the power 12 atoms of carbon. We have one atom of carbon which is of carbon 14. So, that is the radioactive isotope, I must say. So, yeah, that is the basic example, very basic application which we generally use in daily life. So, that is the graphite pencil. and that's how you can calculate the average atomic mass. So there is one more term which is associated with that particular part, which is the isotopic effect. It's better to discuss that isotopic effect in case of organic chemistry as well as in case of inorganic chemistry. And that isotopic effect, whatever I'm talking about, this isotopic effect is actually very, very prominent when we are considering 1H1, 1H2 generally, means protium as well as deuterium. You can also consider tritium, but its percentage abundance is actually very, very less again. So basically this is the factor, because when we are moving from this hydrogen protium to deuterium, you can see the increment in the mass twice, which is the maximum, because when you are moving from carbon 12 to carbon 13, it's not twice, the increment is not twice, it's less than, like very, very less. It's approximately, I can say you are moving from 12 to 13, so difference is 1 by 12 multiplied by 100. But in this particular case, you are moving from 1 to 2, it means you are just increasing the value twice. So in that case, the actual atom becomes heavier. When the atoms becomes heavier, all the rate of reactions which depends upon the heaviness of that particular part, they are going to be affected. It's not going to affect the I can say the chemical properties that much, because they are going to show same type of properties, and chemical properties depends upon generally the electron transfer, and they have same number of electrons. But if I talk about the rate of reaction, which depends upon the heaviness of the atom which we are using, so that rate of reaction is going to change it drastically. Their bond formation is going to change it drastically, and you can see a change in their reaction rate, and that's how you can say that this particular part is actually involved in the reaction, that atom is involved in the reaction, which is for the organic conversion. We generally say that this proton is coming from the solvent, this proton is changing its position. So that's how you can identify that which proton is coming from the solvent part and which proton is changing its position within the same molecule. Because in that case, if something is coming from the outside part, definitely you can see a change in the reaction rate if you are changing that particular solvent or your particular external agent. And that's how you can talk about the isotopic effect. So definitely we are going to discuss that particular part in inorganic chemistry as well as organic chemistry pretty well, because that part is very, very, very important, I can say. Okay, so that is the basic idea about the isotopes. In the same way, if I talk about the next part, we are talking about the concept of isotones. So always remember, in that case, we are talking about all the elements in which number of neutrons are actually same. So isotones are the atoms of different elements with the same number of neutrons, but in that case their mass number is going to be different. If we are talking about the different elements, definitely their atomic number is also different. So you can see in this case Z as well as A, they are different, but A minus Z is actually same, because A minus Z corresponds to number of neutrons, and this part is going to remain constant. I hope the entire part is clear. For example, you can take silicon, phosphorus and sulfur. In first case of silicon, you know the number of neutrons are 30 minus 14, which is 16. In this case also we are talking about 31 minus, sorry, this is 15. 31 minus 15, because phosphorus has atomic number 15. So 31 minus 15, which is again 16. And in this case again, you know, 32 minus 16, which is again 16. So in every case you can see the number of neutrons are exactly same. In case of potassium as well as calcium, their atomic number, their mass number are different, but number of neutrons 39 minus 19, which is 20, and value 40 minus 20, which is again 20. So they are exactly same. In the same way, if I talk about the tritium part as well as helium, again in this case you can see n value 3 minus 1, which is 2, and 4 minus 2, which is again 2. So they are exactly same, and that's how you can differentiate isotones. I hope the entire part is clear to everyone. Very simple explanation, very simple. Now next part is isobars. Basically in this case they have different atomic number, but their mass number is going to remain same. So all the atoms of different elements having same mass number but a different atomic number are actually known as your isobars. Now in this particular case we can say isobars have different number of protons and neutrons and electrons, but the sum of protons and neutrons, which is the number of nucleons, they are exactly same because their mass number is same. So that's how you can actually differentiate isobars with isotopes as well as isotones. Now, if I talk about the examples, again you can see that we have argon, potassium as well as calcium. In each case you can see in argon we have the mass number which is 40, potassium has 39 as well as 40, so we are considering in this time 40, calcium is again 40. Same case with the tellurium, we have xenon as well as barium. Again in each case you can see the mass number will be 130. I hope these three parts are clear. They are very basic: isotopes, isobars as well as isotones, which corresponds to either mass number or number of neutrons or their atomic number. Now the next things are actually very interesting. First one in that case is isodiphers. So what is the meaning of isodiphers? Atoms having same isotopic number. First part is atoms having same isotopic numbers are isodiphers. But the thing is, sir, we don't know what is isotopic number. So isotopic number is very easy to calculate. It is nothing but actually the difference of n minus z, or I can say the difference between the number of neutrons and number of protons. So the difference of number of neutrons and number of protons, if that part is the same, then we can say we are talking about the isodiphers, something new, something new. So mathematically, always remember isotopic number is basically n minus z, where n is the number of neutrons and z corresponds to number of protons. Or I can say a minus 2z, where a is mass number minus 2 multiplied by z, which is your atomic number. So that's how you can calculate the entire part. Okay, I hope this portion is clear to everyone. You can take any example. So we have uranium, thorium, we have potassium as well as fluorine. So in case of this potassium as well as fluorine, let's take the example of these two parts. So we can say in a case of a potassium, which is K39 and 19, the isotopic number will be equal to A, which is 39, minus 2Z, 19 to the 38, that will be equals to 1. In case of 19F9, okay, the isotopic number is basically equals to 19 minus 9 to the 8, which is 18, that is again 1. So isotopic number is the same in both the cases. In this particular case we have 30, 60, 58. So that will be in case of a copper. If I am calculating this particular part, the isotopic number will be 65 minus 58. That will be, I guess, 7. In this particular case, the isotopic number will be 55 minus 24, 48. That will again be 7. So you know, like these difference are actually same in both the cases. You can calculate this particular part and let me know what is the isotopic number in case of uranium as well as thorium. Okay, I hope this portion is clear to everyone. This is the basic idea about the isodiphers. Now next thing in that case is isosters. So basically the molecules having same number of atoms, also same number of electrons, are actually known as isosteres. Now in this case they are different from isoelectronic species, because isoelectronic means, definitely we are going to discuss that part also, isoelectronic means only same number of electrons, but in this case we are talking about the same number of atoms also. So in this particular case there is one more addition related to isosteres. So we have same number of electrons as well as same number of atoms. So for example, if I talk about N2, 2 atoms, first of all in this case we have 2 atoms. In this case also we have 2 atoms. It's not necessary that they should be same. We are looking to the number of atoms if they are same. Okay, it's not necessary that they should be exactly same. N or CO, this type, they may be different, N as well as C and O, but the number is going to remain same. Now number of electrons, in this case nitrogen has 7 electrons, 7 multiplied by 2, which is 14 electrons. In this case carbon has 6 electrons, oxygen has 8 electrons, it means again 14 electrons. So they are exactly same. It means they are isosteres with each other. CO2, in this case we have 3 atoms. In this case again we have 3 atoms. Okay, first part. Now if I am talking about the number of electrons in this particular case, electrons are basically carbon has 6, oxygen has 8 multiplied by 2. So 8 to the 16 plus 6, which is 22. In this case of N2O, electrons are, nitrogen has 7 multiplied by 2 plus 8. So 14 plus 8, which is again 22. So you can see like they are exactly same. One important example in that case is organic benzene, which is your normal benzene, and inorganic benzene, which is known as borazine. So in this case, okay, sorry, the formula is slightly different. The formula is slightly different. Let me take this particular part, and what can we do? We can use something very interesting. Let's say, okay, so basically in this case the formula will be B3N3H6. that is the formula of inorganic benzene or borazine. Now in this particular case, if I talk about C6H6, we have total 12 atoms. Now if I talk about the total number of electrons, carbon has 6 electrons multiplied by 6, hydrogen has 1 electron multiplied by 6. So that will be 36 plus 6, which is 42 in this particular case. In case of inorganic benzene, which is B3N3H6, we have again 336 plus 6, 12 atoms. We have 12 atoms. And if I talk about the electrons, boron has 5 electrons multiplied by 3, 7 electrons multiplied by 3 plus 6 multiplied by 1. That will be 15 plus 21 plus 6. Again we have 42 electrons. Okay, 21, 26, 36 and 6, 42. Yes, 42 electrons. So they are exactly same. So that is the idea about the isosters. I hope this entire part is clear to everyone. Very simple analysis related to each and every part. So we have discussed about the isotopes, we have discussed about the isobars, isotones, we have discussed about the isodiaphers, we have discussed about the isosters. Now it's time to discuss about the next portion, which is your isoelectronic species. In this case, we are only concerned about the number of electrons in any type of species, irrespective of the number of atoms which are present. Okay, so always remember, in this case we are talking about the species. They can be atoms, molecules, ions, anything having same number of electrons are actually known as your isoelectronic species. For example, if I talk about this particular part, this will be much more clear in the periodic classification, because there is a specific relation of isoelectronic species with their radius. So in case of first part, let's say I am starting with N3 negative, which is an ion. So nitrogen generally corresponds to 7 electrons. 7 are already there. Minus 3 means it has gained 3 more electrons. So 7 plus 3, it means we are talking about 10 electrons. In the same way, if I talk about O2 negative, in this case 8 electrons are already present. 2 negative means 2 extra electrons. That corresponds to 10 electrons. If I talk about neon, it has 10 electrons already. The atomic number is 10 in this particular case. If I talk about Na positive, positive means loss of electron. So earlier it had 11 electrons, minus 1, that will be again 10 electrons. In case of Mg2 positive, you see 12 is the atomic number, so 12 electrons were earlier, but plus 2 means it has lost 2 electrons, it means again 10 electrons. And that's how you can compare the entire part: N3 negative, O2 negative, F negative, Ne, Na positive, Mg positive, Al3 positive, CH4, carbon has 6 electrons, 4 hydrogen means 4 electrons more, 10 electrons, NH3, 7 plus 3, 10 electrons, H2O, 8 plus 2, again 10 electrons, and HF, again 9 plus 1, 10 electrons. So every species is basically isoelectronic species in this particular case. P3 negative, S2 negative, Cl negative, Ar, K positive, Ca2 positive, again they have 18 electrons, so they are isoelectronic with each other. In the same way, if I talk about this particular part, we have some more examples: H negative, He, Li positive, Be2 positive, Co, Cn negative, N2, we have N2O, CO2, CNO negative, each have same number of electrons, so they are also isoelectronic with each other. I hope this entire part is clear, because it's a very interesting portion as well as very simple portion, so so that you can actually correlate with the entire part. Okay, now coming back to the same concept, we were discussing about the nature associated with a particular particle, because we were talking about the electromagnetic radiations. So there was a concept which is related to the Planck's quantum theory. So we are going to sum up that entire part in the last portion, that what is actually quantum theory, which is Planck's quantum theory. That is not the initial phase of the quantum mechanical model, that is entirely different, but that particular quantum theory actually talks about the quantization of electromagnetic radiation. They actually has energy in the discrete portion in the form of small packets, which are actually known as, each packet actually known as quantum. Okay, now actually they were working on the electromagnetic radiation. The main idea was electromagnetic radiation. We have to understand what is electromagnetic radiation. So they knew that we are talking about the electron movement, and electron is a charge species. This charge species is going to create some pulses of electric field. These electric field pulses, they are going to create magnetic field and so on. So they are going to move in the direction of propagation, and every field is perpendicular to each other. It means we are talking about the electromagnetic radiation. Now we were looking at the energy associated with them, and they found out that energy is not continuous, just like a normal wave which is explained by the classical physics. It is entirely different. So there was one experiment which is black body radiation, and second experiment was photoelectric effect, which actually corresponds to the same thing, that in that case of electromagnetic radiations, energy is actually emitting, or whatever energy is associated with that electromagnetic radiation is not continuous, but it is actually discrete in the small packets. And that is the basic origin of your theory. Now if I talk about the basic analysis in that case, first of all we have to understand what is black body radiation. Okay, I'll try to explain this particular part in the layman terms as possible. So whenever we talk about any type of a body, when we see any type of body and whenever any light is falling, any type of radiation is falling on that particular body, we generally see three important phenomena. Either some of the part of that radiation is going to be absorbed by the material, or some of the part is going to be reflected by the material, and some of the part is going to be transmitted by that particular material or that particular body. This is the very simple phenomena. Whenever any type of surface of the object is irradiated with some light, then we know that some of the amount is going to be absorbed, some of the amount is going to be reflected, and some of the amount is going to be transmitted. That is the very basic portion related to the interaction of any type of radiation with the surface of a particular object. Now the experiment actually started with the heating of iron rod. But the creation of a black body was entirely different. So the experiment is very simple. You all know this particular part by heart because you all must have seen that experiment, that we are heating the iron rod or any iron object. You know, when we are heating the iron object at a very high temperature, generally it emits certain amount of radiations, and it appears to be red in color. That's why we generally use a red hot. So because it emits a red color, and you can see it's going to be very hot. After some time, you can see if we are increasing the temperature further, it actually changes its color to approximately white. And again, when we are heating it to a very high temperature, it changes again its color to blue. And that is the basic idea. It means when you are increasing the temperature, first of all, the color of that particular part, the object which is your iron rod, it is actually changing. It means that iron object is actually emitting certain amount of radiations, certain amount of energy in terms of their radiations, and these radiations comes under the visible region so that we can see. And 𝐄𝐍𝐆𝐋𝐈𝐿𝐿, you know, that violet to red part. If you are talking about the red part, we have the maximum wavelength and minimum energy. I'll talk about that particular part, how you can relate energy with wavelength. But generally we know that 𝐄𝐿𝐿 is having R part, red region, which is in the wavelength of approximately 650 or 700 nanometer, and the blue region, which is the initial portion, which is approximately in the range of 350 or I can say 300 nanometers. Okay. So when you are heating the iron rod and increasing the temperature, the color is shifting from red to blue part. It means it's emitting certain amount of radiations. It means by increase of temperature, its energy is going to increase, because we are moving from 700 nanometer to approximately 350 nanometers. So the energy is also shifting. So that is the basic idea of the generation of a black body radiation. And scientists simply said that if we can create any type of body which either can absorb entire amount of energy which is provided to that particular body, or it can re-emit the entire amount of radiations, that body is the ideal black body. So they simply said that ideal body which emits as well as absorbs radiations of all frequency uniformly is actually the black body, and the radiations which are emitted by that particular part are actually known as black body radiations. I hope this part is clear. Although this was the animation, but now it's not working because I have converted the entire file into PDF. So that's my bad. But the setup was very easy. It simply is showing that we can create any type of body into approximately equal to the black body, which is I can say 99% of the black body, by simply coating the surface with carbon black, which is very black, so that whenever light is coming inside this particular part, whenever the light is coming, any type of radiation is coming to this particular part, it can strike to this surface, then it will move its direction to this part, then it will go 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 to this part, and then it will go to this part, then it will go to this part. It means due to the internal reflections, multiple internal reflections, the entire amount of energy or this radiation is going to be absorbed by that particular body, and we can actually create 99% of black body with the help of the same coating, which is carbon black, which is actually very black. So due to the internal reflections, and when the light is passing through a small hole, so due to internal reflections, it's going to be absorbed by the entire body, and definitely if the energy is going to be absorbed, it's going to emit the entire amount exactly. So that is the ideal black body situation. Okay, now if you can compare the entire part, like if you can correlate with the entire experiment which I told you, the heating of iron rod. So basically the experiment was heating of iron rod. First of all, there are multiple factors which are changing in this situation. So initially you can see a red color, then you can see a white color formation, approximately white, then you can see a shift in the blue region. It means you can see the color is actually changing with the increase of temperature, So when the temperature is increasing, you can see the red region is approximately 750, or I can say it is 700 nanometer. I'm not saying like it's going to be exactly equal to 700, but approximately equal to 700 nanometer. And this blue region is approximately, let's say, 350 nanometer. Let's say. So the color is shifting from the increment of temperature. So temperature increment is actually decreasing the wavelength. Definitely, that is the basic idea which is happening. Now if the energy is actually in the continuous form, if this body which is iron rod is actually a black body, I can say, so it's going to emit the energy with the increment of the intensity. That is the basic idea. Now what happens for a particular perfect black body? It simply says that whatever radiations it's going to absorb, it's going to emit same amount of energy exactly. All type of radiations, whatever that body is absorbing, it will be able to actually emit the same type of radiations. It means on increasing the temperature, there will be no effect on the change of the color. If the color is throughout red, it should be red, whatever thing is happening. If I'm increasing the temperature, if I'm decreasing temperature, it's not going to occur. It's not going to change the color of the entire radiation. The color should remain same, but the intensity should increase. The color intensity should increase. But this was not in accordance with the black body, because if the energy is coming or it's going in the continuous form, it should show the same type of behavior. But you can see this type of curve. Now in this case, both intensity and frequency of the emitted radiations depends upon the temperature, because we know like this is the actual part. Now when you are heating that iron rod, you can see that the wavelength is going to decrease. First of all, the wavelength is going to decrease at a lower temperature. At lower temperature, you can see this type of radiation. You can see radiation in this region. Okay, but at higher temperature, you can see the shift in the color. This wavelength corresponds to the color. In this temperature, let's say the color is coming as red. but in this temperature this color is coming as blue. Now it means by increase of temperature, first of all the wavelength is changing because the color is changing. Now the intensity of a maximum radiation is also changing. Initially the intensity of the red color was not that high, but the intensity of the blue color was very high. It means the intensity as well as frequency. Frequency means we are talking about the relationship of lambda also. Okay, so these two things are changing. It means it is not in correspondence to the wave theory part, because wave theory simply says if you are changing the temperature, it's not going to matter. The same color will become more and more intense because the radiation type is exactly same. Radiation type is exactly same. It's not changing. So this is not in accordance with the wave theory. Now there are certain explanations regarding the black body radiation. So you can see at a given temperature, the intensity of the radiation emitted from a black body increases with a decrease in the wavelength. So basically the meaning is it should increase with the decrease in the wavelength at a particular temperature. So let's say in this case temperature is constant. Temperature is constant. So at a red hot iron case, let's say the temperature is fixed, which is let's say 2500 Kelvin, or I can say 3000 Kelvin, whatever it is. In that case, the red color is fixed, means it's going to emit all the radiations, but the red color is the most prominent one. It means at a given temperature, the intensity of the radiation emitted from a black body increases with a decrease in the wavelength. It is actually increases the intensity. You can see this is going to increase with the decrease in the wavelength, but to a certain extent. It's going to increase to a certain extent. It's going to achieve the maxima, then it's going to start decreasing. It means you can only see the color which is having maximum intensity. Definitely that iron, red hot iron is going to emit all the radiations in all the color range. You can see it's going to emit blue color range radiations at a particular temperature. It's going to emit green color radiation. It's going to emit white color radiation. It's going to emit your red color radiations. But you can see only red color because the intensity of that red color is actually maximum. It means the intensity reaches to a maximum value at a given temperature, and then it starts decreasing with a further decrease in the wavelength. But this maximum part, this maximum intensity part is responsible for its color. It is basically responsible for its color. Okay, that part is clear. Now when we are changing the temperature, I can see that intensity is changing, but the maximum color, the maximum intense color is also shifting. Definitely with the increase in the temperature, I can see that this wavelength is again going to shift. But in that case, this maxima point now corresponds to any other type of color. So as the temperature of the black body increases from T1 to T2, the frequency of the emitted radiation is going to increase, definitely, because wavelength is shifting, and the intensity of the emitted radiation also increases. It means that energy actually is changing both intensity as well as frequency. So we cannot say that for every type of radiation, the entire amount of energy which is provided by that particular radiation depends only and only upon the intensity. It is actually depends upon the frequency part. It is also depends upon the frequency part, which is not in accordance with the your wave nature or wave theory, classical wave theory. Okay, so you can see that now the red color is actually shifted to the blue color. But if I am comparing the temperature at 3000 Kelvin, red color was less intense, but at 5000 Kelvin, the blue color is actually very prominent. It is very intense. It means this wavelength is decreasing. It means the frequency is increasing, because you know that frequency is equal to C upon lambda. This particular part is constant. It means frequency is inversely proportional to lambda. If the wavelength is decreasing, it means frequency is increasing. So by increase of temperature, it means you are providing the energy. So whatever radiations are emitting, again in terms of energy, their energy depends upon the frequency as well as it depends upon the intensity. I hope this entire portion is clear to everyone. I hope this entire portion is clear. Now from that particular part, you can say according to the wave theory, according to the classical wave theory, the energy of the electromagnetic radiations is proportional to the intensity, but it is independent of its frequency as well as wavelength. So whatever temperature I am using, it's not going to affect that type of radiation. So let's say the body is going to emit a specific type of radiation, let's say red color radiation, and I'm changing the temperature. If I'm increasing the temperature, according to wave theory, that red color should not change because the energy is continuous. If it is not in the small fraction of packets, it's continuous, and whatever intensity is appearing due to red color, it's not going to change when I'm increasing the temperature. When I'm increasing the temperature, it means there is a slight change in the energy packets. Initially, more packets of red part are emitting, but after increasing temperature, more energy packets of blue color they are emitting. So we can say, according to the classical wave theory, energy of the emitted radiation is actually only and only proportional to the intensity. If we have less temperature, less red color is appearing. If I am giving more temperature, more red color should appear, but it's changing its color. So this is not in accordance to the wave theory. Now we can say the radiation emitted by the body being heated should have the same color, or I can say the wavelength or frequency throughout, but it did not happen. It means the wave theory is failed to explain the black body radiations. Although there are different type of curves, I can say the curve which I showed you is basically the ultraviolet catastrophe, and there is one more part which is a Vane theory, corresponds to black body radiation. There is also one curve which is a Rayleigh curve corresponding to the black body radiation, but I'm not going to go deep into that particular part because that is not relevant. I'm just giving you the basic idea that what is black body and why that particular theory, the classical theory of a wave nature, was unable to explain the entire part. Because every time I am changing the radiation, I am changing the temperature, it means the packet of energy, the radiations which I am providing or the radiations which are emitting, they actually have a different packets of energy. And if these packets are different, it means the wavelength or frequency corresponding to these two packets, they are going to be different. And that's why you can see two different colors. That is the basic idea of your black body radiations. So definitely for that particular understanding, we need Planck's quantum theory. So, you know, like for that particular part, we need Planck's quantum theory. I hope the entire portion is clear to everyone. I hope I will be able, or I was able to explain you the entire concept of black body radiation with the simplest way possible. Okay. Now, the next effect is basically a very prominent effect, which is your photoelectric effect. Again, this photoelectric effect clearly shows the particle nature. So what is happening in the particular photoelectric effect? First of all, let's try to understand the setup. So in this setup, you have again glass tube. Glass tube in this case is connected to two electrodes, and they are connected to a battery, so that you can check the current is appearing in this particular case. The one electrode in that case is basically your metal surface, and the next electrode is basically your detector, which can detect the upcoming electrons, and these electrons can be checked by the ammeter. So that is the basic setup. Now in this setup, I am actually subjecting a particular type of radiation on the metal surface. Okay, when this light of a particular frequency or particular wavelength is going to strike on the surface of a metal, two things can happen. So let's say this is your metal surface. This is your metal surface, and I am subjecting a particular light on the metal surface. Okay, this is your radiation, I can say. If it is a radiation, it means it has a specific frequency and wavelength. Okay, done. Now next thing is, it may be possible that on detector side, you can see electrons are actually striking, electrons are actually coming, or it may be possible that when I am again using the radiation, in this case you can see the detection, it may be possible, or in this case you can see no detection. This is also possible. Now what is happening in this particular case? These are the two scenarios. I already told you these are these two scenarios. Either you can see the detection of current appearing, or I can say the detection of electrons, or you cannot see any detection. Okay. Now in this particular case, we are considering, let's say that there is the detection of electron happening. So what is the photoelectric effect? We can say that photoelectric effect is nothing but the ejection of electrons from the metal surface. When a light of a suitable energy, or I can say suitable frequency, strikes on the metal surface, and that phenomena is actually known as your photoelectric effect. And these electrons which are emitting from the metal surface are actually known as your photoelectrons. So that is the first part, very basic portion related to the photoelectric effect. Now in this case, you can see we have a specific metal. I can change this metal and I can change this radiation. So basically the entire part of a photoelectric effect depends upon the first part, which is energy provided as well as metal surface. Okay, it depends upon two parts, whatever energy I am providing in terms of radiations, and it also depends upon the metal surface I am using. Now the basic idea related to photoelectric effect is very easy. The basic idea related to photoelectric effect is very easy. First part, you need incident light or incident radiations. You need incident radiations. It means this is the part of energy provided. Second part, you need a metal surface. You need a metal surface. Third one, you need a detector, or you need emitter, I can say. Okay, so these are the three parts which are required. Now in this particular case, what is happening? Let's say I am providing energy. So this is the energy provided, and if we are providing energy, which is the source, this is the source. What is the use of source? Source is providing the energy. It means if it is providing the energy, it has a specific frequency as well as wavelength. Done. Now this energy provided can be utilized in two parts. First one is the ejection of electron from the surface. Okay, it is useful for the ejection of electrons from the surface. Now this ejection of electron depends upon the metal surface I am using. This depends upon the metal surface I am using, because on the metal surface, you can see these electrons are attached on the surface with the positive kernels. That is the metallic part. Metallic bonding is basically the force of attraction between the electrons, like metal kernels which are present in the sea of electrons. So there is a force of attraction between these two parts. This energy, whatever I am providing, if that energy is sufficient to break that particular bond, if that energy is sufficient to break that particular bond, to break force of attraction, if whatever energy I am providing, E provided, if that is enough to break that particular bond, so you can see just the ejection of electron. You can see the ejection of electron. If that energy is not able to break that particular bond, if this energy provided is not sufficient, so you can see no ejection of electrons. Very easy. First part is clear. And this ejection of electron is actually has given a new term which is known as work function. This particular part is work function denoted by phi. Okay, first part. Now let's say this energy provided is more than the energy for the ejection of electron. Let's say the radiations have a more amount of energy which I am providing, that is going to overcome this force of attraction, and again some part is going to remain as it is, some part is extra. So that extra energy is utilized by ejected electrons for their movement. So the electron movement is basically nothing but your kinetic energy. Okay, that is your kinetic energy. I hope this part is clear. This is the very basic of your photoelectric effect. I hope this entire part is clear. Just have a look at it and then we will discuss the next portion. Okay, now we know that we have certain source which is going to provide the energy, and if this energy is actually having a greater amount, we have extra amount of energy, some part is going to be utilized in the ejection of electron and some part is going to be used by the electron for its movement, which is the kinetic energy, which is basically the kinetic energy of the emitted electron. Let's say this energy is not sufficient. First of all, there will be no ejection. If there is no ejection, you can see there will be no kinetic energy and there will be no current flowing in the entire apparatus or the setup, whatever you are using. So that is the first part. Now in this particular case, the first important thing is that every type of a metal surface has a specific type of force of attraction that depends upon the metal to metal, which is going to change. But that energy which is binding the electron with the metal surface is actually having certain amount of energy in it. If I am providing exactly same amount of energy to that particular part, that is going to break that force of attraction and electron will be ejected to the surface part. So in that case, always remember that light must have some energy that enables the electron to overcome the attractive influence of the nucleus, and that part we are talking about the work function. That is basically the work function, which is your phi. Okay, so let's say I am providing energy provided having frequency which is nu. Now for this movement, because we have to discuss the Planck's quantum theory, but remember I am giving you one formula of energy, that energy of electromagnetic radiation actually depends upon its frequency. It is directly proportional to the frequency of that particular radiation. Always remember. So we have the formula of energy which is equal to h nu, where h is the Planck's constant, or I can say the proportionality constant. It has a specific value also. Okay, so this is the part of energy relationship and we know that nu is equal to c upon lambda, so we can say that energy will be equal to hc upon lambda. One more equation from this particular part. So this particular portion is related to your electromagnetic radiations. Okay, just remember this particular formula, just note it down. We will discuss that part in the Planck's quantum theory. Okay, so we know whatever energy we are providing having the value of frequency which is h nu. So we can say E provided will be equal to h nu. E provided will be h nu. Now in this case, this work function is basically the frequency. I can say there is some amount of energy and energy is related to frequency. So there is some frequency which is the I can say the minimum amount which is present between the electrons as well as your metal kernels, which is attracting, or which is the positive attractive influence of the nucleus, and that much amount of energy is needed to break that particular bond. So always remember this E provided, first part, that this E provided should be greater than phi. It should be greater than phi. If this particular part is greater than phi, then we can say we can see the ejection of electron, and it can be equal to phi. But if that particular part is equal to phi, then only you can see the ejection. There will be no kinetic energy because the entire part of energy is already consumed in the ejection of electrons. Okay, so this is the first part. So you can say that E provided should always be greater than phi or equal to phi, so that you can see the ejection of electron. If this E provided is less than phi, then you can see there will be no ejection of electron. I hope this part is clear. Very simple portion. Okay. Now from that part we need to understand what is the work function of metal, because that depends upon the type of metal which we are using. So basically the minimum amount of energy which is actually required to eject the electron from the metal surface. So basically this is the E is directly proportional to h nu. If we are talking about the energy, that we are talking about the minimum amount of energy. Minimum amount of energy we are talking about in this particular case. It means we are talking about the minimum amount of frequency. It means we are talking about the minimum amount of frequency. So we can say that minimum amount of energy which is required to eject the electron is basically your work function. If that is the energy minimum, we can say the value is equal to the ionization energy of the metal, because in this case we are talking about the ejection of electron, and there is one important term in the inorganic chemistry which is the ionization energy. Ionization energy simply talks about the ejection of electron from the outermost shell of an isolated gaseous atom. So whatever energy we are providing, if that is capable of breaking the bond or breaking the force of attraction between the last electron and the nucleus, we can say electron is going to lose, the atom is going to lose the electron, and that corresponds to the phenomena of ionization. So that is ionization enthalpy. So always remember the value is equals to the ionization enthalpy or ionization energy. If this energy is very high, for some metals this energy is going to be very high. So those metals cannot easily eject the electron very easily, because we have to provide that much amount of energy. Now metals having low ionization energy can easily undergo this phenomena. So definitely for the phenomena of photoelectric effect, we always choose those metals which can show this phenomena very easily. It means those metals which have a very less value of ionization enthalpy, like we have potassium, like we have rubidium, like we have cesium. This is the most important part, cesium as well as potassium. They are generally used for this type of application. And there is one more application which is the application of solar cell, that actually works on the phenomena of photoelectric effect. So I'll talk about that particular part very soon, but that is the first part, which is the work function. Now in this case the work function is also correlated to the frequency, because we are talking about the energy. So I can say the minimum frequency required to eject the electron from the metal surface is actually known as threshold frequency. This is the most important term now, and this threshold frequency is denoted by nu naught. This is denoted by nu naught. So always remember that energy provided, which is h nu, should always be greater than or equal to your work function, which is phi, and this phi will be h nu naught. That particular, nu naught. Okay, that should be greater than nu naught. So you can say that frequency whatever I am providing, it should be greater than or equal to nu naught. Then only you can see the ejection of electron. I hope this entire part is clear. Now let's say this energy provided is actually much more. It is more than the frequency, minimum frequency which is required to eject the electron, and definitely electron is going to eject from the surface. Remaining part of energy is going to be absorbed by the electron and it's going to start moving. So if I am providing more amount, it's going to move very fast. If I am providing maximum amount of energy, it's going to move just like your flash, that very fast, because the energy provided is utilized in two parts. First one is the ejection of electron. Ejection of electron is done. Now whatever extra amount of energy is present, that can be absorbed by the electron so that it can move very fast. Okay, so that is the basic idea of the entire equation. So next part is basically your kinetic energy of the photoelectron. If the energy of the light falling on the metal surface is actually greater than its work function, then the remaining energy will be converted to kinetic energy of the emitted photoelectron. That's it. That's it. So that's the part. Now in this particular case, always remember that total energy whatever we are providing is utilized in two parts. First one is the work function and next one is the kinetic energy. So we can say that this energy provided is, let's say, h nu, that will be equal to phi plus kinetic energy. So from that particular part we can say that kinetic energy will be equal to h nu minus phi. We know that phi is equal to h nu naught, so we can put the value here in this part. So kinetic energy will be h nu minus h nu naught and kinetic energy will be h nu minus nu naught, where h is basically the Planck's constant. It has a specific value. Definitely we are going to discuss that particular part after a few slides. So that is the basic idea about the photoelectric effect. Now there are certain things which are actually very much required. So what are the factors which are going to affect this entire phenomena? I can change the frequency of the emitted radiations, sorry, incident radiations. I can change the frequency, or I can change their intensity. So how the entire part is going to be affected with the help of these changes? Let's try to find out. So first part is the effect of a frequency. Frequency means directly energy. Frequency means directly energy. So for each metal, there is a certain value of frequency below which photoelectric effect does not take place. This is the threshold frequency. We know that particular part. If I am providing more amount of frequency or more amount of energy, it means every type of electron, whatever present on the outer surface, they are going to absorb that energy. They are going to eject their surface and definitely they start moving, because this particular part is going to affect the kinetic energy. This particular part is going to affect the kinetic energy. If the energy provided is below the threshold value, no ejection will take place. If that is equal to the threshold value, then you can see the ejection of electrons. If that value is more, you can see the kinetic energy. If you are providing more, kinetic energy is going to increase. So you can simply say from that particular part that kinetic energy of these electrons increases with increase in the frequency of light. So you can see this, this is the most important part, that it's going to affect only kinetic energy. So if you are providing the amount of a frequency, you can see you can change their frequency. If you are changing the frequency, if you are increasing the frequency, you can see the kinetic energy is going to increase. In that case, the electron, they are going to move very fast. They are going to move very fast. Okay. So this is the first part. It means the kinetic energy is going to increase. Now if I talk about the curve, definitely there is minimum value from which kinetic energy should start. That is the value of nu naught, that is threshold frequency. That is threshold frequency, because below threshold frequency nothing is going to happen. Above this threshold frequency, you can see the increase in kinetic energy drastically of that particular electron. Okay, so that is the first part. Now the second case is effect of intensity. Now always remember, this intensity always affects the number of electrons ejected. So the number of electrons ejected is proportional to the intensity of the light. So always remember, this depends upon the number of electrons ejected from the surface. So definitely if I am increasing the intensity, I can only see that more number of electrons are actually going towards the detector part. So you can see that kinetic energy is going to remain same. Kinetic energy is not going to be affected. With the increase of intensity, you can only see that more number of electrons are now emitting from the surface, which was not in the case of previous part. So let's say I am providing a specific amount of energy. Let's say this is the E provided. Now in this case, this frequency is fixed. this frequency is fixed. This frequency is fixed, and this frequency I am already saying that this is more than nu naught. It means you can see that ejection is going to take place, kinetic energy will be happening. Now in this case you can see that kinetic energy is going to remain same. Kinetic energy is not going to change, because whatever energy I am providing, I am just increasing the intensity. Definitely earlier, like it was falling on a specific region, now it's falling on a larger region. It means now more number of sites are actually subjected to the incident radiations. It means more number of electrons are going to be ejected from that particular surface. Earlier the case was different. You can see a small portion of metal surface is incident to a particular light, is subjected to the incident light. Now you can see by increasing the intensity, more area is available for the ejection part. So you can see in that case kinetic energy is going to remain same, but number of electrons ejected, it's going to increase. I hope this entire part is clear to everyone. So you can see there will be no change in the kinetic energy when we are talking about the intensity part. I hope this entire phenomena is clear to everyone. Now before discussing the questions, let me just give you the basic idea about the Planck's quantum theory, because this particular part is required for the calculation. So according to Planck's quantum theory, he simply said that when we are talking about the electromagnetic radiation, so basically in this case when we are talking about the electromagnetic radiations which are generated by the moving charged particle, these radiations are slightly different from the wave nature. In case of wave nature, you know that entire energy is basically continuous, there is no break. But in this particular case, you can see that this energy provided is not in the continuous form, but it is present in the discontinuous form. So you can say energy is emitted or absorbed by atoms or molecules in discontinuous manner in the form of small packets of energy, which are known as quanta. So this is the first point related to your Planck's quantum theory. So that's why these electromagnetic radiations are slightly different. Now in this particular case, in case of light, when we are using this entire phenomena for light, we say that quanta is actually termed as photons. Okay. Now the next part is relation of these energies with their frequency. So always remember the energy of each quantum. So one energy packet is basically your quantum. So the energy of each quantum is directly proportional to the frequency of the radiation. So that particular part actually relates to the frequency of the radiation. So you can say that E is actually equals to, or E is directly proportional to nu. So if I am removing the proportionality, it becomes E is equal to h nu. Nu is a C upon lambda. So we will get the final equation as E is equal to hc upon lambda. I hope this entire part is clear, where h is basically your Planck's constant having the value. I told you it has a specific value which is 6.626 multiplied by 10 raised to the power minus 34 joule second. Okay. Now if we are putting the values at approximate consideration, you can say that energy will be equal to 12400 divided by the lambda, which is in angstrom, and this should be energy should be in electron volt. So this is a simplified formula for calculation, but otherwise you can use this formula much more often. I hope this entire portion is clear to everyone. That is the basic idea about the radiation. Now always remember the radiations, whatever emitted or whatever absorbed by the any type of body which we are considering, is again the total amount of energy whatever we are considering emitted or absorbed by a body is actually whole number multiple of a quantum of radiation, or I can say quantum frequency of radiation, which shows the quantization part. Quantization has a specific meaning. It's talking about the discrete values. Just like your stairs, when you are moving up or you are moving down, you have like a specific energy, then down, then a specific energy, then down, then a specific energy, then down. If I'm talking about the continuous part, you can see the slides. So this is the slide nature, continuous, which is continuous. So this is a discrete part having a specific value at each point is basically the quantization part. So you can see this energy, total energy is actually equals to whole multiple of each quantum energy, which is h nu. So you can say that will be E is equal to n h nu, which is the total energy, and n is basically the integer. It can be 1, 2, 3, whatever it is. So you know, we talked about the quantization of charge earlier, where the actual charge in the Mulligan experiment, where the charge was multiple of a specific value, which is 1.6 multiplied by 10 raised to the power minus 19. So Mulligan thought that the actual charge of one electron should be 1.6 multiplied by 10 raised to the power minus 19. So that is the basic idea of quantization, which is the discrete nature, not in the continuous form. So this shows that if I am talking about the discrete nature, it means I am considering particle nature, not the wave nature, because if it is wave, you can see the wave is continuous in nature. So this electromagnetic radiation has the tendency to show particle nature also. Okay, now coming back to the questions of your photoelectric effect, because we have covered the entire concept of Planck's quantum theory. Now question says calculate kinetic energy of emitted electron when light of a wavelength which is 300 nanometer falls on the metal having 3 electron volt work function. So in this case, work function first part, which is phi given, that is 3 electron volt. Now either you can convert this entire part into joules by multiplying the entire value with 1.6 multiplied by 10 raised to the power minus 19, because 1 electron volt means 1.6 multiplied by 10 raised to the power minus 19 joules. So either you can convert this entire part into joule, or you can convert the next part, whatever you are calculating, by dividing it with 1.6 multiplied by 10 raised to the power minus 19. So we have calculated this particular part, which is 4.8 multiplied by 10 raised to the power minus 19. Now the next part is nu of the radiation is given. Okay, wavelength is given. Okay, wavelength of incident part is given, which is 300 nanometer. So we can calculate the value of E provided, that will be Hc upon lambda. Okay, H is 6.626 multiplied by 10 raised to the power minus 34 multiplied by 3 multiplied by 10 raised to the power 8 divided by 300 multiplied by 10 raised to the power minus 9. Okay, so that will be 6.626 multiplied by 10 raised to the power minus 34 multiplied by 10 raised to the power 8 multiplied by 3 divided by 3 multiplied by 10 raised to the power minus 7. So 300 multiplied by 10 raised to the power minus 9 is 3 multiplied by 10 raised to the power minus 7. So I can solve this entire part. This is done. And then 7 and 8 will be 15. So that is a 6.626 multiplied by 10 raised to the power minus 34 plus 15. So 15, 15, 30, 15, 19. So that will be 6.626 multiplied by 10 raised to the power minus 19 joule. We have the energy provided. So you know the formula that kinetic energy will be E provided minus phi. So that will be 6.626 minus 4.8 multiplied by 10 raised to the power minus 19 joule. That will be your final answer. Very easy question, very simple question. Okay, I hope this part is clear. Okay, now moving to the next part. Okay, very interesting question, although this question is from JEE Advanced. The work function phi of some metal is listed below. The number of metals which will show photoelectric effect when the light of 300 nanometer wavelength falls on the metal surface. So basically you have lambda provided, which is 300 nanometer. Can you calculate the energy provided? Yes, we can calculate, that is Hc upon lambda. Okay. Now from that particular part I can say we have 6.626 multiplied by 10 raised to the power minus 34 multiplied by 3 multiplied by 10 raised to the power 8, 300 nanometer, which is again 3 multiplied by 10 raised to the power minus 7. So this 3 is going to be cancelled out. We have 6.626 multiplied by 10 raised to the power minus 19 joule. Same part, just like the previous question. So this is the energy provided in joule, but this work function you can see is given in electron volt. So I can convert this energy provided in electron volt, which is 6.626 multiplied by 10 raised to the power minus 19 divided by 1.6 multiplied by 10 raised to the power minus 19 electron volt. So this is going to cancel out. If you can solve this particular part, let's save some time. Let's try to use calculator. Sorry, you don't have to use the calculator, but I am using just because of the time constraint. That will be 6.626 divided by 1.6. So that will be 4.5. 4.14125 electron volt. That is the value which is coming after solving the entire part, which is the energy provided. Now we always know for ejection of electron, the E provided should be greater than or equal to phi. This is the basic idea. So every value should be greater than of this part. E provided is 4.14125. So in this case, phi is less, definitely ejection will take place. In this case, phi is less, ejection will take place. Phi is less, ejection will take place. Phi is less, ejection will take place. Now in every case of copper, this phi value is more than E provided, and if this phi value is more than E provided, then you know what is going to happen. In this case, no ejection. No ejection of electron takes place. So this phi value is more, phi value is more, phi value is more, phi value is more, phi value is more. So we have only 1, 2, 3, 4. So we have only lithium, sodium, potassium and magnesium which has a less phi value. It means the question is asking about the number of metals which will show the photoelectric effect. So the answer will be only 4 metals are capable of showing this type of effect. And that's how you can solve the advanced question also. So very easy question. But this was asked in JEE Advanced. Okay, I hope the entire part is clear to everyone. Very simple question. Next part is a metal was irradiated by a light of a frequency 3.25 multiplied by 10 raised to the power 15 second inverse. The photoelectron produced has its kinetic energy 2 times the kinetic energy of the photoelectron which was produced when the same light, same metal was irradiated with a light of a frequency 2 multiplied by 10 raised to the power 15 second inverse. What is the work function? So very interesting question, very interesting question. Okay, so we can take the first case. Where that this nu provided is basically 3.25 multiplied by 10 raised to the power 15 second inverse. Okay, okay. The photoelectron produced has kinetic energy. So in this case, let's say the work function is phi, which is, let's say, x. Okay, and in that case, let's say the kinetic energy 1 in this particular case will be h nu minus x. Okay, that will be h multiplied by 3.25 multiplied by 10 raised to the power 15 minus x, that is the kinetic energy 1. Okay, now let's take the second case. In this case, the nu provided is basically 2 multiplied by 10 raised to the power 15 second inverse. Okay, again phi is same because the metal is same. Okay, now in this case, kinetic energy 2 will be h multiplied by 2 into 10 raised to the power 15 minus x. Okay, so that is the basic idea. Now it says that the metal was irradiated by the kinetic, the photoelectron produced has its kinetic energy. So in this case, the kinetic energy 1 is actually 2 times of the kinetic energy which is irradiated by the light of second case. So this kinetic energy 1 is a 2 times the kinetic energy of 2. So if the 2 has kinetic energy, let's say whatever value, the first has twice amount of value. So kinetic energy 1 is h multiplied by 3.25 multiplied by 10 raised to the power 15 minus x will be equal to h 2 multiplied by 10 raised to the power 15 minus x, and this entire part is multiplied by 2. So from this particular part, you can say that we have 3.25 multiplied by 10 raised to the power 15 h minus x will be equal to 2 2s are 4 multiplied by 10 raised to the power 15 h minus 2x. Okay, so that will be, I can say this 2x will be on this side, so x will be equal to 4 minus 3.25 multiplied by 10 raised to the power 15
multiplied by h. So we can say that will be 0.75 multiplied by 10 raised to the power 15 multiplied by h.
So that will be the value of x, and we have to calculate the work function, that is the value of work function. So you have to let me know the final answer. 0.75 multiplied by 10 raised to the power 15 multiplied by 6.626 multiplied by 10 raised to the power minus 34. That will be the value of your phi part. Okay, so let me know the answer in the comment box as a homework. Okay, I hope the entire portion related to photoelectric effect, Planck's quantum theory, everything is clear to everyone. I'll give you certain question as a homework for the Planck's quantum theory. Just try to solve those questions, and in the next session we are going to discuss the next portion which is related to the atomic models, because up to this portion everything is very basic. We discussed about the particle nature, we discussed about the black body radiation, photoelectric effect, terms associated with the atoms, we discussed about the basic idea of fundamental particles. Everything is clear. Now from that portion we are going to discuss about the atomic models, how atomic models were defined, how they were created, and how we actually reach to a particular point, which is the origin of quantum mechanical theory. That is the most interesting part. Okay, so I hope everyone enjoyed this session, learned something new from this session. Remaining part will be discussed in the next lecture. Okay, so that's all from my side. Thank you so much.